So just to say something a little bit more about Philip Young, I had hoped that Philip Young would be able to join us today. Philip is my colleague, the co-founder of Digital Futures back in 2011. He's a professor and now associate dean at Tongji University, Shanghai, where we've held many of the events regarding digital futures. Well, all apart from last year, we went online. And this year, he will also be hosting a series of workshops. There'll be collaborations going on with ICD Stuttgart, ETH Zurich, IAC Barcelona, and so on, which will be hybrid studios alongside some straightforward online studios. And just to say, over the course of the years, there has been a series of experimentation, especially in regard to material intelligence. That is to say, rather than saying the intelligence, material intelligence as such, but rather the intelligent use of materials. This is a bridge, first of a series of bridges that were produced, one each year. This is Patrick Schumacher on the bridge testing it out. And this was like the second 3D printed bridge in the world. And each year there's been exploration about how we can use different techniques, software techniques, to explore the possibility of different forms of bridge. That was the following year, and then last year with Matthias, who's here on the side, on the top here, Mark Burry, Andy Clark, myself, Philip Yuan, and a few others. So this will be happening again this year. Material intelligence. So just to kind of emphasize, what we're talking about here is not as though materials are intelligent in themselves. I think the term smart materials has been used. I would say materials have properties, and there are intelligent ways in which one can use materials. To say that a material actually has an intelligence is maybe incorrect, but one could put that sense of intelligent use of materials alongside the use of computation to model and simulate the behavior of materials, to see that there is a new paradigm emerging in which we are applying forms of intelligence to understanding how we can handle the material behaviors and the structural behaviors of buildings. That said, this is a publication that we produced 2017, Digital Fabrication, and I would say that actually the title is possibly slightly wrong. Aki Menges is one of the editors there. Can you digitally fabricate something? Well, you can. What the digital does is to effectively control the fabrication process. Materials are analog, and you could argue that the whole way in which we put together buildings is that the digital remains a kind of a form of modeling. Buildings themselves are not digital, buildings are analog, but we use digital means to control the production of these things. And this is a comment by Neil Gershenfeld, where he kind of makes the point clear that what we're dealing here is with cutting, grinding, and so on, very much analog processes that are controlled by the digital. So the term CNC, computer numerically controlled, is really the term that is very useful to understand precisely what is going on. So in terms of AI then, this is the work of AI Build. It's not as though AI is constructing it. What AI is being used in this case to control the nozzle in the 3D printing process. So I guess we should have called that book maybe robotic fabrication rather than digital fabrication, or rather digitally controlled fabrication. So I want to go back just to contextualize some of these ideas within history, and particularly to the publication Digital Tectonics, which I think is quite crucial in the context of today's debates. Back in the turn of the millennium, in 1999, I was teaching at Columbia in New York, where there was interesting kind of debate going on between the very progressive computational guys like Carl Chu, Greg Lynn, and so on, and maybe the slightly more conservative historical figures such as Kenneth Frampton. And Frampton's book, Studies in Tectonic Culture, could be taken in some way as a kind of critique of the work that was going on in the computer at the time. I mean, formally exquisite work, but Frampton's argument essentially is that the architecture is a question of tectonics, of how you put together materials in different formats and so on. The book Digital Tectonics was an attempt to kind of reappropriate the term tectonics and to understand it as being an important kind of part of how we're operating these days, in a sense that opposition between the digital and the tectonic had begun to collapse as increasingly people were using computation to understand material behavior and structural behaviors. This was a book that was co-edited with David Turnbull and Chris Williams. Chris Williams appeared on Digital Futures a few weeks ago, and we were all colleagues at the University of Bath at the time. And incidentally, this conference that we organized, one of the young students in the audience at the time was a guy called Akim Menges. So there we go. And this is the kind of work that was coming out from Columbia in '99. This is the work of Carl Chu, exquisite work. I mean, really astonishing work, very quite revolutionary in many ways. But it was even Carl would be very clear. It was very open about this. This is work what he calls in vitro, in the test tube, as it were, in the vitrine, behind the computer screen, not in reality. And exquisite as this work is, it has no material understanding or structural understanding of forms of behavior. So the crucial break happened in many ways. I think this was the first. I'm not sure, but this I think was the first building that used computation to understand structural behavior. This was a building by Foster and Partners. The roofing in of the courtyard in the British Museum in London, where the challenge was to go to create a glass roof that would span from the rotunda in the middle to this slightly irregular courtyard on the outside. And the real challenge here was the fact that they were dealing with an existing structure that had no capacity to withstand any lateral loads. The engineers for this project were Bureau Happold, and Chris Williams was himself the consultant for this particular project. And what they basically did was to produce something that was, first of all, it was using an algorithm to describe the form. This initial algorithm produced these kind of ski jump-like edges, which were not controlling the thrust very well. So the next one was then, this was the more refined version that eventually was used. And the second technique was to, as it were, to massage this form on the computer using a technique called dynamic relaxation technique, which was pioneered by another colleague of mine of ours at Bath at the time, Mike Barnes. So if you were to look at this kind of the ridges that appear in the kind of mullions in this roof, what happens when you apply this technique, it smooths them out. So you will go from here this to that. So using these two techniques, they were able to create what effectively was a kind of lid that would literally sit on that roof without creating any lateral thrust. And you can see by the nature of these vertical stanchions that they were kind of that it was just literally sitting like a roof, like a lid. Parallel to this particular project, there were other forms of research going on. This was a very early form of structural software called iForm that unfortunately hasn't been marketed, but this was developed by Christina Shea, who was teaching at the AA at the time, a lecturer at the University of Cambridge. She's since gone on to, I think now ETH Zurich. And this was a form of a stochastic non-monotonic form of simulated annealing. Annealing is the process whereby you cool steel down in a controlled fashion so as to increase the strength. And the stochastic non-monotonic side was about trying to open up. So each time there was a different version came out. These things would take about 20 minutes to run, and you'd have a range of different outcomes. You then would choose between your outcomes. And this was the first built version of this, a collaboration, which I mentioned before, in Amsterdam, between myself, Spiele Vedechnik, Christina Shea, and a few colleagues. Where we built this for the first time. I mean, this might seem, at the time it was revolutionary. I mean, this is what, 2002? Things have changed a lot since then, but this was kind of pioneering work in many ways. The crucial figure, and this is not really a session on philosophy as such, but the crucial figure in this particular conference was Manuel de Landa, who has espoused this doctrine or theory of what he calls new materialism. I like to think it in terms of and I'm not sure he would agree, but in terms of rethinking of Marx's famous dictum, up until now, philosophers interpreted the world, the point is to change it. In order to change that world, we have to understand the material conditions in which the world is operating. And de Landa famously produced a series of books. This was hugely inspirational book for me personally, 1,000 Years of Nonlinear History, where he takes this approach and applies it to the way that cities are developed over time. A truly astonishing and revolutionary book, to my mind, far more significant than Learning from Las Vegas. And DeLanda has had an incredible influence, I think, all over the world. He was teaching, when I was at USC, I brought him to USC to teach. He's been teaching in the East Coast at Columbia, at UPenn, at Pratt, and so on, and also the European Graduate School. And he's been, I think, behind a lot of a kind of crucial figure behind many of the important architects today. Again, we're going to next semester be talking about philosophy. I would simply say that Gilles Deleuze is the important philosopher behind Delander's work. And it's fair to say that Delanda has a particular take on Deleuze. This is Delander's Deleuze. He strips away the Guattari and just works on Deleuze and maybe simplifies Deleuze. Well, he does simplify Deleuze. Whether he oversimplifies, I'm not sure, but it certainly makes Deleuze accessible. In his article for Digital Tectonics, he was talking about the use of or experimentation into metallurgy and drawing upon some ideas in A Thousand Plateaux by Deleuze and Guattari, especially the chapter on the war machine. And I don't want to go into this too much detail, but suffice to say, one of the ideas that is sketched out in the war machine is the idea there are two different modalities of thinking, which can be illustrated in architectural terms between the difference between what Deleuze calls the Romanesque. I take it to mean the classical in general. So it could be the Renaissance or the classical itself, and this is a view of a Brunelleschi interior, and the Gothic. And the difference is this: the Renaissance, the classical version, is essentially based on representational logics and following certain templates. It's about the visual less than the structural. Of course, it does work structurally, but the rounded arch is not necessarily as efficient as, let's say, the Gothic arch. And it's about a kind of top-down way of thinking in some senses where you follow the rule book. Deleuze refers to this as the major sciences, the kind of authorized version that you follow instructions, as it were, whereas what he calls the Gothic is really a form of experimental work, where you're seeing the world not in terms of representation, but in terms of processes. So understanding the world in terms of not of aesthetic templates like proportions of the human figure, but rather in terms of forces and flows. Understanding the thrust of the way in which the weights are taken down, the flying buttress, kind of very cleverly containing the thrust within its fabric. And this was seen as an experimental way of operating. Of course, many of the cathedrals collapsed in the process of building. And in Delander's own contribution to digital tectonics, he was talking about the difference between Robert Hooke as an experimental practitioner who developed his theories about elastic behavior versus someone like Sir Isaac Newton, who was the kind of the establishment figure. So if Robert Hooke stood for the kind of the minor sciences, for the experimental, for the Gothic, so in some senses, Isaac Newton stood for the major sciences, for the kind of the authorized way of doing things. Anyway, one can see this idea of the Gothic, which is not so much to do with the Gothic as such, but more with a kind of certain way of thinking, expressed throughout examples in history. This is, of course, Gaudi's Sagrada Familia, and we know from Mark Burry about how incredibly sensitive Gaudi had been to kind of questions about structural performance, and we know also about the hanging weight model, which was used to define the form of some of his buildings. And of course, if you were to turn that catenary arch upside down, you get this form which is used in compression throughout Gaudi's work as well. Likewise, and here I kind of, in a sense, opening up to ICT Stuttgart, Frei Otto, whose Institute of Lightweight Structures is so close in some ways to what Achim is now doing. Frei Otto was not computational in the digital sense, but he was using materials to compute form, using spiders' webs, bubbles, and so on to understand form. And here is this famous at the bottom right here, the Munich Olympic Stadium on the top right there, and he was very much a kind of pioneer in his time. I would say very much misunderstood in an age when people were interested in form rather than formation. Frei Otto was really a pioneer. And he was coming out of Germany, of course, after the war. He'd been a fighter pilot during the war. Germany was a place full of scarcity after the war, and he was using these intelligent techniques to use materials ever more efficiently. And of course, these days also we have this kind of ethical imperative to be more efficient with our own buildings. Since Patrick is also here, maybe just mention briefly some of the research work that's been going on, which I think is also fits very much within this this particular way of thinking that illustrates that there is a kind of a whole trajectory throughout architectural culture, architectural history, that has been exploring the possibility of the intelligent use of materials, especially in structural forms such as this. And finally, I'd mention also the work of Cecil Baumann. Here, an installation in the Tate Modern in London with Anish Kapoor, where the form of this structure is coming out of a morphogenetic approach. It's a form-finding approach. It's allowing the material, and the only force on this particular the fabric of this thing is gravity itself. An astonishing work. And one way to kind of think about this difference, which in Deleuze's terms is the difference between the hylomorphic and the morphogenetic, is to think about the difference between the work of, say, Frank Gehry on the left-hand side and this transport interchange by UN Studio, for which Cecil Baumann was the engineer. And they might look similar, these two forms. They're curvilinear forms, but the point is that on the left-hand side, Gehry's is very much kind of molded, formed in a way, the top-down way, whereas on the right-hand side, this form comes out of an understanding of structural behavior. They look similar, but they're very much part of very different traditions in many ways. And then, I mean, just a kind of final comment on this kind of thing about form. What I would argue is that we in architecture tend to have a very kind of slightly shallow understanding of complexity in terms of visual complexity. If you were to compare a bubble, which Delander talks about the soap bubble and how it almost magically generates its perfectly spherical shape, it comes out of a way to understand how a soap bubble is. The soap bubble is far more complex than the image on the left hand side. I put briefly, it's been a kind of material computation that's been using that's the result of the difference between internal and external pressure, the surface tension, and so on and so on. And to my mind, I'm not well. At the time when I wrote this, there was nothing that one could do computationally to simulate the complexity of a simple soap bubble. And finally, we can now see another generation of this coming through in the work of Philippe Bloch with his Rhino Vault, where he uses software to understand material behavior and avoid the stress as much as possible to produce these extraordinary structures. This from the Venice Biennale that has the kind of the ratio of the thickness of this vault is similar to that of an egg, extraordinary in its own way. And then some 3D printed slabs that he also has worked on. This one highly reminiscent and of the kind of work that was coming out in Cambridge, about 1450, King's College Chapel, the fan vaulting there, and so on. So let me stop sharing. So just a reminder that the call for papers for the Digital Futures Conference is out, and submission is the 15th of April. And I'd like to invite Dylan to share his screen. The order today will be Dylan, followed by Yassi, followed by Nick Bell. Welcome, Dylan.
Thanks a lot, Neil. Just 1 second, and I'll share. Okay, is that good?
That's great.
Okay, great. Well, thanks for the very poetic introduction, I guess, to the topic, Neil. I think you probably spend more time than us thinking about this from the theory perspective. So hopefully we can give sort of complementary, more detailed technical version of this story. So I just wanted to first say that I think it's really nice to somehow be back in this context after Tiffany and I already in 2018 did this workshop, which we also called Material Intelligence at the Digital Futures conference, where we were looking at how we could, let's say, program different levels of compliance into 3D printed structures. That was quite fun, and as always in Shanghai, somehow motivating in terms of effort and spirit. And this is something that this work is something that has also somehow transisted and continues in our group even today. So
Just one thing. There's a slight interference there. I don't know if there's any way of avoiding that.
okay, in the sound or in the
sound, yeah.
in the sound. Okay. One moment. Maybe we can try switching the microphone. Does that help?
Yes, yes, much better. Yeah.
Okay. All right. Great. So anyway, I think we're well placed in this sort of context of material intelligence. And well, we didn't name our group that actually in Stuttgart. It very much follows the same lineage of thinking. So what we did name the group that I lead is material programming. And so I think first today we want to give a sort of very brief introduction of what we mean by material programming in terms of concept and how it relates to our work. So I'll start by explaining basically where we are, not physically, but usually, let's say, in pre-COVID times. So I lead a small research team within the Institute of Computational Design, made up of myself, Tiffany, Laura, and Yazi, who will present later in the lecture today. And we are all PhD students at the Institute for Computational Design and Construction, which is led by Achim Menges at the University of Stuttgart in southern Germany. And more we operate in parallel and overlapping with two clusters of excellence, the integrative computational design and construction, which we chair, and further and sort of more recently with the living materials cluster at the University of Freiburg. So material programming is a term that is maybe often confused with things such as programmable materials or smart materials, or even material intelligence. But we want to explain a little bit how we come to this terminology. So we are actually all architecture students in our group, and we sort of come from this architectural lineage, despite the fact that now we are primarily studying engineering, I would say. And so we like to, of course, always start by placing this in the architectural context. When we look at Louis Kahn's somewhat famous, maybe it happened conversation with a brick, where he asks the brick what it wants to be, and the brick says that I would like to be an arch. And what I find somehow fascinating about this conversation now in the current context is that, well, we might somehow always know that a brick structurally would like to be an arch, and someone like Philip Bloch could explain to us how to design structures in which bricks or masonry units are effectively used in arches or domes. We still inherently seem to leave out the question of how the brick would actually become the arch physically. And we also look at this through some of my other personal heroes, Ray and Charles Eames, which have a relatively simplistic look about design as a plan for arranging elements in such a way to best accomplish a particular purpose. But different from their 1950s, 60s, 70s view, we really are interested in how tools for design and also construction give new meaning to this statement. So when we think about construction and innovation in construction, I think we usually frame it in this idea of a synthesis between the automation and the machine building, like an industrial robot, and more so the material. And this is something that I would argue that we actually already see in many ways. So in China, I'm sure that this is even more prevalent, but even in Middle America, it's now not uncommon that we have robotic factories that build buildings, especially with timber. So I would argue that the automation dominated by the industrial robot is actually already there. And in a couple of ways, there are examples in which the material tends to play a slightly larger physical role in its formation, like in this case, with the curved crease folding of sheet metal, where the bending is inherent to the shape in which the robots manipulate the material to. And I guess generally, from a contrary perspective, we can describe this relationship relatively simple, that there's an input. In the case of a machine, this is usually a design input or a locational input, which is then computed into a plane or a position of the robot. And then there is a physical output, which is a combination of the robot moving and the material following it, usually by brute force. So this could describe a lot of the processes in which you mentioned earlier, Neil, that are more commonly known as CNC. So computer numerically controlled processes. And what's interesting is that these almost always use pure force. So it's a robot either subtracting material from something existing or bending it into a new shape, or in the best case, probably adding multiple smaller pieces of material to build something up. And what our group is really interested in looking at is how we could actually invert this relationship. So rather than always thinking of the synthesis starting first with the robot doing all of the work, how the material could actually play a larger lead role in influencing its shape. And maybe the best example of this is from some of my very early work at the time when I finished my master's in Stuttgart, where we have here, for example, a sheet that is again curved crease folding in terms of geometry, but simply by programming the direction and the arrangement of the pieces of wood, by drying it out or changing the moisture in the piece, we can actually generate a physical shape without any brute external force applied. And this is something, this sort of concept of material programming and self-shaping in this case is something that we really do take from nature in many ways. So maybe the best example that Achim Menges would always use to explain this is with a spruce cone, which is representative of many types of plant cones on Earth that actually open up when they fall down from the tree and are cut from the supply of the living tree, and they perform a passive motion in their scales in order to release their seeds. And this is something that's amazing geometrically and functionally, because the tiny scale of the pine cone, I mean, we have tons of them in our office and in our home offices. Every single one of these scales can perform this sort of sophisticated geometric motion without any energy or any motors or a computer. So we have somehow millions and millions of pinecone scales that are operating incredibly reliably all over the world every year. And it's doing this like simply based on the composition of the fibers inside of the scales. So this concept is something that we studied for many years at ICD, predating my team or my group, specifically looking at how we could program wood composites to respond to the weather. And this is something that Yazi will talk about a bit later in the presentation, and so we'll leave it at that for now. So before we talk about how these types of things are applied in architecture through our work, we have to introduce some relatively simple concepts of how we would program wood. And I think this is also well, graphically relatively simple here, it also ties into what Neil introduced with Manuel de Landa. So in this case, rather than the machine having an input of a numeric position or electricity, the input here is just water. And wood as a material is actually already, I would argue, programmable. So we're not giving it any new features. The wood materials itself has the ability to sense, compute, and actuate towards an output, which is a change in volume. And almost every type of wood has the ability to do this. But what's really, really amazing is that it can do it with such high swelling force and contraction force. And this really puts it on a different level compared to many of the synthetic smart materials that you might be familiar with as an architecture student or a mechanical engineer even. And normally this is seen as a defect. So your table splitting apart if you leave it outside, or where I'm from in northern New England and also throughout the UK, with shingles that tend to crack or warp towards the sun as the exterior surface dries out and is then hit with water. And like the pine cone, this ability to change shape with the input of moisture happens in wood in the microfibrils of the cell walls. So it's a sort of inherent natural property of the material, which we can actually never really take away. And in industry, this is usually seen as a relatively negative thing, which causes pieces of wood, when we cut them, to do things like this at a large scale, like spring, bow, cup, twist. And this is all based on the way in which the wood is cut from its natural geometry. And what we said, like very early on, so this is from my master thesis, is how could we look at this not as a defect, but really as a sort of feature that we could curate or sort of program in a way, first digitally and then physically, in order to create a desired change in shape, rather than these sort of awkward moves. So we add to our chart here with wood, if we look at something like a wood bilayer, which is just simply 2 layers of wood, and we add another really simple input parameter, which is the orientation and the arrangement of the pieces of wood within a larger mechanism, we can use the same programmable effects to generate not just volumetric change in shape, but curvature in specific directions. So this is what it looked like really early on as a master's student in Stuttgart with really very little money. I was able to purchase a piece of beech wood for, I don't know, 120 euros. We cut it up. We use our own software to figure out where these triangles should be oriented within the part. And then we put them back together into a part that has then specific orientations, starting with a specific moisture content. It looks really, really simple to begin with. It's like a puzzle. We use CNC machining, but we could have also cut them by hand if we didn't have the machine. And what we get is this dramatic change in shape just by removing or adding moisture to the system. So in the early prototypes, this movement is relatively awkward. So it's not necessarily always predictable, but what I find somehow amazing is that, while the in-between states might be kind of awkward, the end state is actually relatively reliable. And this happens without any machines, without any additional energy going into the system. And if we start to imagine how a robot might shape something like this, even at the meter scale, I think we start to see the value and the simplicity of the approach. So that brings us to, I think, the major project from an architectural perspective that I want to share today. So this is called the Urbach Tower. And this is a collaboration, as always, between ICD and ITK at the University of Stuttgart. And it was greatly aided by a scientific collaboration that we established with the Laboratory of Cellulose and Wood Materials at EMPA and ETH Zurich, as well as an industry partner with Bloomer Lehmann from Switzerland. So again, I think it's always so important to mention that these are relatively large teams that execute these projects. It's no longer the sort of Starchitect alone. And these teams are also relatively diverse. So they include nearly traditional craftsmen and engineers, as well as material scientists, which is something that I think we have developed in the University of Stuttgart as a sort of now relatively normal way of working, but internationally, I would say is still pretty unique. So the concept for this project also starts with a sort of industry standard that we see that wood is undergoing a certain type of renaissance as a building material, but it usually ends up with these straight boxy forms, which are nothing like what Frei Otto or Buckminster Fuller would have, let's say, imagined in 2020 or beyond. And while it is sort of adding to the sustainability of the way in which we build, it comes at the sacrifice of this relatively standardized types of architecture. And at the same time, we know from basic architectural education at USC even, that curved surfaces tend to be more efficient structurally, and they can carry more load with less material. And of course, we can build curved surfaces with wood, and this is not necessarily something that's entirely new. But the way in which we make these curved surfaces has developed a lot differently from the way in which we design with them. So, well, designing a BIM model that can go straight to production digitally is maybe no longer nearly as complex or as expensive as it would have been 10 or 15 years ago. The way in which we produce the material has not necessarily advanced so much. So even though we have these automated systems to bend wood into 3D shapes, the cost of production is nearly double for a curved beam of that of a straight beam. And as we get into more complicated surfaces and twisted types of geometries, this relationship goes up exponentially. And in the end, this means that we simply don't use curved pieces of wood as geometry and architecture nearly as much as we could. And so if we go back to our self-shaping wood, which I shared earlier, the question here was how we could turn this into an industry-adapted process in which we could shape the pieces of wood hygroscopically during the pre-fabrication and use this to, in this case, produce larger sheets that have a relatively high curvature, but remain a slender in thickness. So the key to this computationally is actually in the mechanics. So this is not something necessarily that we do, but that our partners at ETH and EMPA are experts in understanding what type of input parameters we need in terms of orientation, thickness, and moisture content in order to produce reliable changes in shape in an industry adapted process. So to put this very shortly, I mean, you can read some of our scientific publications about this if you want to know more detailed, but we need a mechanics model. We need also a materials model. And then we need a way in which computationally to define all of the parameters as we move into more complicated geometries. In the end, this means that we get a certain model that allows us to be able to predict the movement relatively accurately, enough so that we can go into producing high curvature pieces for architecture. So this is the site of the building. It's relatively isolated, so there's no power at the site, and it's only marginally or partially accessible by car. Once we have these types of high curvature, thin wood elements, the question from a structural point of view was how we could use them most efficiently to generate a tower. So the first slide at the top here shows this study that we conducted with the ITKE, which is really enabled by the fact that we can get a pretty high curvature in larger sheets. And on the bottom is this sort of architectural overlay of this, looking at how we can create a double curved overall geometry, still using single curved cylinders. So geometrically, almost everyone would tell you that the tower is double curved. That's not true. It's made from a set of single curved cylinders that are intersected at an angle. So in terms of a parametric model, there are actually only two parameters in this overall geometric model. It's relatively simple, and I would challenge anyone to try to be able to build it within a couple of hours in Rhino or Grasshopper. As a constructional system, it's a little bit more sophisticated. So of course, once you have curved pieces and you're able to produce them, the most difficult thing becomes how can you connect them without needing a lot of steel. So here we have a sort of variable model of screws, which we can use that then become hidden between the 12 different components and are almost completely invisible from the inside of the tower. And that relies on the fact that our partners from ITK can not only model the behavior of the CLT down to the different layers and panels, but also look at almost every single screw throughout the connection details that are all at variable angles again, and that they can not just model this, but they're able to iterate through multiple design options relatively quickly to find a solution that works for everyone. So now we move, I guess we'll speed up a bit through the production of how this works. So I think this is maybe the most important image that I will share today, because, well, as architects and computational designers, we can develop all of these relatively sophisticated models in the computer. This is what material programming is to me. So this is a guy in the factory in Switzerland who then has the task of sort of hybrid manually sorting out the material based on the criteria that our really complicated mechanics model was able to define. So he's actually able to read the moisture contents and some information on the screen, but he still does this a little bit by feel and a little bit by his experience. And it's also maybe interesting to point out that already 2 years later, this production hall has been phased out and replaced with an automated sorting facility. So here you can see what he sort of sees, and then he makes a relatively hybrid human computer judgment about the material. And then the boards that we need for each layer go into this sorting wheel, and then they're sorted out. And of course, when we work with natural materials, the sort of data and the sorting looks something like this. It's never a perfect line or a perfect, let's say, graph. But it does mean that we're able to sort it well enough that we can produce these larger bilayer sheets that have 2 layers and are pressed together. And then they're placed into a kiln. And inside the kiln, a drying process occurs, which we need anyway to use timber in construction, and the 3D form is generated. And this emerges through a relatively normal process that happens in industry. So while here we do need to still use energy to dry out the wood, what's maybe most prominent about this from the industry point of view is that all of the shaping happens in parallel compared to when you would use a mold, and every single piece needs to be shaped on the mold in sequence. And it's also, while we did not explore so much variation in geometry, it's nice to point out again that we could potentially program a different curvature in every single one of these sheets. And when they dry out, they would go to these specific curvatures. So then the panels get taken to a different hall and turned into these blanks from which the larger CLT components for the tower are cut. This involves basically gluing them together in multiple layers and sort of overlapping them or arraying them to form larger sheets. And these in the end are the finished components. We still do have to use a CNC machine to trim them and put in the tiny edge details, but you can imagine this process kind of like going to a dentist, that you want the CNC machine to do the least amount of drilling and carving as you possibly can. So in the end, I think each piece required only 90 minutes of machining, which is relatively small for a 14-meter long piece. Then these get put together into assembly groups, and a facade is added from larch wood. And then they're assembled on the site, in this case, in just 8 hours by a team of 4 workers. Compared to the construction the foundation, which took almost 2.5 weeks. The structure is almost entirely wood. We have this very thin 12mm steel ring at the top, which forms an interface between the structure and the roof, and also provides a sort of grounding for the lightning protection system. And then this is topped off with a transparent roof. We haven't yet started working with transparent wood, but I think there are some companies in France that we would really like to partner with on making that also out of wood. So architecturally, why we're so interested in this is because we also think that it shows a sort of new light on how we can use more sustainable materials. So while wood we've worked with for many, many years, this is a type of geometry that we get with these really sharp curves on the inside and almost pillow-like surfaces on the interior. That is something that's very different in terms of architectural expression. At the same time, it's really, really performative structurally because the whole tower is made from just 90mm thick CLT, even though it cantilevers from the ground without any steel in the actual structure. It's also really nice that the structure remains friendly. So without any paint or any treatment, this can be basically like touched by anyone, even a child. So it's a bit different from some of our carbon fiber structures. And it retains this kind of natural beauty, which also alludes to its performance. So the tower sort of continues to live in this natural setting. We have to keep monitoring it. So this is always really important to note that these experiments continue long beyond our sort of quick introduction of them as a research pavilion or as a demonstrator building. So the moisture content in the wood continues to change every day as it's exposed. And this is something that we monitor for the next 2 or 3 years and compare to 3D scans of the building to understand how it might change shape over time globally. And while this is how we sort of imagine the structure in this beautiful landscape, I think we also can't necessarily ignore how it's perceived in the public. So from everything from comparing it to something that Bernie Sanders would not want to pay for, to Bill Baker visiting, to children sort of climbing on it, I think it's very interesting to see how these things live as well in culture. It's also kind of interesting. I think this is maybe the highest honor that we're compared now to a Ferrari in terms of value or worth, at least in a joking state. So we've taken a material which is usually considered to be something that we would build any normal house out of, and we've turned it into something that is seen as being as expensive as a Ferrari. And the building will stay again for a couple of years, and we will keep monitoring basically how it ages and also how it's perceived. So then just very briefly, I want to introduce the new project that we have, which is about furniture that we will be releasing relatively soon. And I think, well, the tower uses self-shaping as a sort of pre-manufacturing step, which is maybe hidden or completely removed from the kind of later life of the building in which it's supposed to remain a static object. Developing a furniture system was really exciting to us because it gave us the chance to look at how this could become an active part of both the assembly process and how we sort of critique and how we live with our furniture. So the idea is relatively simple, that this represents a sort of extreme flat pack configuration where pieces are produced in a flat configuration in the factory and tuned to the specific geometry that you order. And then once you're inside your house, you open them up, and over a couple of days, they shape into this geometry. And this shaping continues to happen at a relatively slow rate back and forth over the lifespan that you own the furniture piece. So this is what it looks in our very quick video. So you open the piece, and then inside your house, this sort of slightly awkward assembly happens, again with no tools, so there are no Allen wrenches, and also let's say you don't need any instruction kit, you just open the package. And then just very shortly, I can share some of our more recent work with students, which looks at how we can see material programming from a slightly different light, where we can consider how smaller machines can be used to activate material behaviors, and really look still at this relationship, not just from the robot operating on the material, but the material as well pushing back. So this is a project from two of my students, Nicholas and Greg, from last year, where they're looking at how these tiny sets of relatively simple robots can actually use the bending capacity of materials like bamboo as a locomotion system to almost propel them through space. And of course, this requires a completely different conception of how robots actually work. So no longer are we programming a specific position of the robot, but we're really trying to understand how the robot can itself learn through simple movements and simple behaviors, how the material bends. So in this case, we have no idea where the robot might actually need to position itself on the piece of bamboo in order to bend it down to meet the other one, or if that's even necessarily the goal. But by developing the sort of online systems and internal intelligence, in this case, if we dare call it that, of the robot, we can get it to do some tremendous things. And this is especially somehow promising to us because it means that we can start to almost reinvent how we would use materials like bamboo, which have historically been kind of cast out, similar to some types of wood from contemporary construction, exactly because they don't meet these sort of millimeter tolerances that are usually required for these types of building. And with that, I think I will pass it on to Yazi. Sorry, it was a bit longer than I thought, who is going to talk about 4D printing and the co-design of bio-based materials and smart structures in our group.
Thank you, Dan. Thank you. That was wonderful.
All right, so should I just share my screen?
Yes, Dylan, you have to unshare yours. Yeah.
Okay.
Okay.
All right. So I will continue where Dylan stopped. So in his presentation, we saw how the cellular mesostructure of the wood works together with the hygroscopic property of the cellulose fiber to create this self-shape and shape changing, from pine cones to the Urbach Tower. Using thinner pieces of wood, we can create wood bilayer structures that react to the relative humidity level in the environment and move continuously in a cyclic motion. This is the research that my colleagues started at ICD more than 10 years ago in a way to look at how we can create shape adaptation in the buildings, specifically building facades, so that we can create environmentally responsive kinetic systems that react and work with their surrounding environment. And a very nice implementation of that we could see in the Hygroskin pavilion, which was built in the Stuttgart. And as you see in the images, there are these apertures embedded on the facade and the surface of this building, of the pavilion, that they open and close in response to the environmental factors. In a sunny day, they are closed, so they provide shading, and when it's more cloudy, they open up so that they can let in natural light. So using wood, they were able to build these structures, and also, as Dylan showed, it's super efficient and effective in a larger scale architectural system. but it somehow comes with some constraints. For example, we know that the wood expands and shrinks perpendicularly to its growth lines. So this means that if we want to reach a specific bending curvature, we need to find a piece of wood that has that built-in fibrous mesostructure. This gets more and more complicated if we want to create more complex geometries or more complex mechanisms. So this brought us to the question that what if we could computationally design and digitally fabricate this internal mesostructure, which in turn defines the shape change in the pieces, defines the bending direction, bending orientation, the timing, etc. And this took us to 3D printing. So with 3D printing, we can construct a part layer by layer, line by line. So we can literally create something like the wood's mesostructure now by defining the direction and the orientation of the fibers, which allows us to literally program the movement and the shape change in the parts. So in our method, we use FDM 3D printing, which is the most standard desktop 3D printing technology. And for this, the material needs to be in form of thermoplastic filaments. But the key here is that they don't need to be pure plastics. They can have some fillers in them. And these fillers are the things that bring hygroscopicity to our material. So in one of our projects, we partnered with another institute at the University of Stuttgart, Institute for Plastics Technology. And they produced hydromorphic filaments for us. They took a matrix of bio-based plastics, and they added cellulose as a filler. And cellulose is the agent that makes these filaments into smart filaments or hydromorphic filaments. And using these, we're now able to 3D print our structures. We usually use two types of filaments. One, the cellulose filled or wood filled filaments that work as the active layers or the active agents. These are the layers that expand and shrink. And we combine these with other types of material, such as normal PLA or flexible material, to create shape-changing structures. So in the first step, the colleagues before me who were working at the institute replicated the exact same apertures that you saw in the Hygroscale Pavilion. This was to benchmark and see if the 3D printed structures behave similarly to the wooden structures and if they react to the changes in the relative humidity level. But then after that, we can get more and more exciting. Things can get more and more exciting, and we can go and create more complex structures. Now that we can 3D print things, we can design and we can program the material with the type of shape change that we wanted to achieve. For example, here you see how different modules with the same outline are bending in different directions. And this is only defined through the arrangement of the 3D printing toolpaths. The key point here is that now that we have this digital design and digital fabrication workflow, we can take advantage of different computational design tools that allows us to design shapes, not as solid objects, but shapes in transition. We can build our own simple shape prediction tool so that we can see and we can design parts before and after transformation. For example, this elephant that is here designed in rhino and grasshopper, and then 3D printed. In the left-hand side, you can see it's on its flat state, which is the state that we 3D printed. And on the right-hand side, you can see it after actuation. So this type of programming goes even beyond programming just a geometry. Shape change is temporal, and another aspect that we can control and we can program is the temporal property of shape change, the speed and the time scale of shape change. For example, here you can see that in this simple aperture design, each of the flaps are programmed to move in different time steps. And this is how we can create the overlaps in the structure and make sure that the parts don't collide with each other. And similarly, with the exact same geometry, it's just different assignment of parameters in different flaps of the aperture that creates an absolutely different arrangement. Here we have two sets of layer. In one layer, the flaps open first, faster, quicker. In the other layer, they open with some delay. And lastly, the other advantage of 3D printing is that we can combine different materials with different properties, and putting that together with our ability to program the shape change, we can create more and more complex shape-changing structures. And the type of structures that I'm going to focus a bit more for the rest of my talk are the self-shaping curved folding structures. So here we use three types of material. One of them TPU filaments, which are flexible filaments, and we use them to create hinges and fold lines in our structure. And then we took the geometry of curved place folding, which combines bending in the surfaces and folding on the curved crease lines to create these beautiful and also functional and efficient structures. So on the geometric side of the curve folding, a crease goes under a fold when the two faces on the two sides of it bend in the opposite convex and concave directions. So in our self-shaping structures, the bending in the faces are induced through this hygroscopic bending motion that we generate with the cellulose filled materials. And as the two faces on the sides of the crease line bend, this makes the crease line to fold. Yeah, in this image, you can see this layered 3D printed structures of self-shaping curve folding structures. As you see, there are many layers with three different types of materials, and each of the layers have their own specific function. Active layer, which expands and shrinks, restrictive layers, which turns the expansion and shrinkage of the active layer into bending, the bonding layers, and the hinge layer. And all of this is possible because we can easily design them and 3D print them using a normal FDM printer. The interesting thing is that now that we create this specific type of geometry or self-shaping curve folding, we can surpass some of the limitations that are inherent to the material. For example, here you see two modules, one of them with curve folding and one of them with simple bending. They're the exact same materials, exact same parameters. With the simple structure, which only bends, we can get maximum around 27% of opening. And when we use curve folding, we can reach up to 70% of opening. And sorry. This is very important when we think of these structures in the context of architectural application. For example, a kinetic facade, that what we expect from it is to provide us the largest margin between open and closed state. Another great thing about this workflow that combines computational design and 3D printing is that by controlling some parameters, by slightly adjusting some parameters, we can program how the overall shape change in the structure happens. And in the curve folding structures, we can easily see that, and we can really take advantage of that to control the maximum folding angle in the folded structures. So yeah, here what you see on, what you see on the right-hand side shows the design space of one single curve folding module. And you can see how the folding angle can be controlled either through geometry of the curve crease, which is shown on the top right, or through the 3D printing parameters, which is shown on the left-hand side image. And now by using these tools for shape programming, we can create structures, for example, as you see here, a modular facade system with 20 something different modules. Each of them have their own unique geometry, but through controlling the parameters, we can reach the same folding angle in all the different modules. Okay, so here now I want to just show you a quick preview of our computational fabrication workflow. What I'm going to show you is for curve crease folding, but this is pretty much the same or similar workflow that we use in different projects. So it starts with inputting some geometry in 2D, goes to the mesostructure setup. This is basically the material programming process. Then goes to 3D shape prediction, and if the shape that is reached after shape prediction, the simulated shape is what we are happy with, we can get the toolpath, we can generate the toolpath and then export the G code and use it for 3D printing. So this is the first step here in the case study of curve folding, inputting some faces and then defining their bending direction and the bending orientation. The next step is generating a mesh and then using our geometric shape prediction tool to see how what would be the result of the mesostructure setup that we defined in the previous step. If some of the fold angles, some of the deformations, transformations are not desirable, we can go back to the previous step and adjust the mesostructure setup. After we make sure that the shape is desired, we can go and generate the toolpaths. So the toolpaths are generated for different materials and different layers separately, and then they all come together and the G code is generated, which is then used in a normal desktop 3D printer for 3D printing the part. And after the part is printed, it's the time for its actuation. So with this specific material that we used here, we put the objects for half an hour in the water. And after that, upon drying, they self-form into their final shape. Here, the curve folding bird. All right, so now that we have this overall workflow, there's basically no limit for us to the level of the complexity and the resolution that we can achieve. And this takes us to some of our studies on the curve folding tessellations. For example, what you see here is a crease pattern that consists of 21 faces and 14 crease lines. We designed this using our computational workflow. We fabricated this. And here you see how it self-shapes from flat state, which is where it was printed, to this final folded structure. And the material does this all on its own. And I think here we can just take a look from some distance and see that if we want to fold that structure by hand or by robot, it would be extremely difficult. By hand, it would require high level of mastery. And if we want to use systems such as robot fold, which is super successful for limited number of folds in a structure, but really can we have 20 robots if we want to simultaneously fold 20 creases at the same time? So this I think is kind of like reaching the point that shows that the method that we do, the way that we embed the self-shaping process into the material itself is like embedding a bunch of robots in the material, and this whole coordinated motion between different parts, different faces, which results in a structure to self-fold without requiring any external forces, any assembly efforts. And these structures, because they are corrugated structures, because they're based on origami tessellations, they are structurally performative after folding. As you see, for example, just the structure on the left-hand side, but the thickness of 1 millimeter and the self-weight of 8 grams, it can take the load of 620 grams after it self-shapes into this corrugated structure. And the same goes on what we see on the right-hand side, where the 1 millimeter structure with 12 grams of self-weight can take up to 300 grams of load. And so this is for us just the beginning of one of the paths of research that we are continuing at the Institute of now how we can use these structures, potentially larger scale architectural applications. One potential would be to use them in sandwich panels and use these structures as a space filler. Another option would be to actually produce them in a much larger scale. And these are the things that will come up in the near future. So just to recap of our overall methodology, we have a co-design between material, mesostructure, and the shape-changing mechanisms. Material is the thing that enables this self-shaping and shape-changing process from the beginning. We customize our materials, we engineer and design our materials together with the application that we have in mind. And since hygroscopicity is our main aim in the context of architectural application, this is how we approached the materials. Next is the mesostructure. This is what we computationally design and digitally fabricate. And this is where we really control the structuring of the parts, which defines its overall shape change. And lastly, there are shape-changing mechanisms, which are the applications of simple bending bilayers of the shape-changing elements that come together that create functions and architectural applications for us. And when we put 3 of them together, we can do awesome things. So this was it from my side. I just wanted to mention that there are some things that we still cannot show in these types of public presentations because they're from unpublished work. But if you're interested, please follow our research. We are going to publish more soon. Thank you very much.
Thank you, Yassi. Thank you, Yassi. That was amazing. There are going to be lots of questions, I'm sure, but let's move on straight on to Nick Bao for the final presentation. Nick.
Yeah, so can you see my screen?
Yes.
Okay. So thanks for invitation, Professor Neil Lynch. So hi everyone. I'm Nick Bao from MIT University. I'm honored to be here to give a lecture at FIU Architecture and Doctor of Design program. So the topic is called Forming Complexity. It is also the name of my architecture design studio at MIT Architecture, and also work with Professor Mike Shea and Roland Snooks in their lab as well. So their lab is called Center for Innovative Structure and Material at School of Engineering, and Roland Snooks' new lab called Tectonic Formation Lab at MIT Architecture. So I just quickly introduce myself. I'm a registered architect and currently lecture in architecture and at MIT and focusing on the architecture technology stream. So today I would like to talking about the performance driving digital architecture design and intelligent construction. So the background and motivation and problems of my research come from three aspects. The inspiration by the nature laws and the collaboration between architects and the engineers, and the lost connection between architecture aesthetics and the structural performance simultaneously. So my research is mainly about the algorithm for functional intricate form and mass customization manufacturing strategies for the construction industry. So start from some precedents like the Gothic buildings and the Gaudí's church, and nowadays the smart slab by ETH and the fiber pavilion by ICD. You can find the similarity, the form all inspired by nature, and especially from the nature structures. And it balances the aesthetics and the structural performance. So how can we make the form from nature, and how can computer generate the nature forms rationally? So in 1920s, Professor Mike Shea proposed a simulation of apple shape optimization. Which is called using the BSO method. It's a bidirectional evolutionary structure optimization. And the structure design, and this is a structure design project by myself and the team, and has won the first prize in the structure optimization and adaptive manufacturing in China. And you can see the material is being removed step by step, and also keep the similar structure performance. And now the method, this topology optimization method has been tested and applied on several architecture projects. And also Professor Mike Shea's team and developed the BSO method into a Reno grasshopper plugin called Amoeba. It also has been selected as the most influenced digital tool for the year at Digital Futures Conference in 2020. So now I want to talk about some architecture application of this method and in my research. So we collaborate with MIT Architecture Robotic Lab and use the architecture robotic lab use KUKA robots to develop the large-scale 3D printing intelligent construction techniques, and use the adaptive manufacturing, including the clay concrete print, mainly polymer print, and the wire metal print. So the first project I was talking about is XForm 1.0. This one is in 2019, and we built this project in Chongqing University at Digital Future Conference. So you can see on the left side of the image, so you can see the tree branch and the Gaudí's tree branch like columns. So we applied the loading on the box shape. then fix the bottom parts and apply the BSO algorithm, then generate the similar looking of the structure. So you can see here, so the top roof structure is quite similar with the Gaudi's church, and also we created more branches for the column system. So you can see the original design is at the left side. Then we run the optimization, creating the tree branches. Then we smooth it. Later we print one small scale 1 to 10 small scale model to test it can be printable. Later we move to the large scale robotic printing to realize the large scale construction methods. So you can see the video. We use the KUKA machine to print the column of a quarter of the pavilion, the columns, and the robotic is this robotic is developed by Roland Snook's team at the research lab. And later we just do some post-production of the columns and delivery these 4 columns and from Melbourne to Shanghai. And this is construction methods, and we work with our digital future workshop students on the construction and assemble it. We're just using like a few hours to assemble the whole structures. So you can see it's about 2.2 meters high and the 1.8 wide. So it's very successfully built up. So the next project is the X-Form 2.0. So this one is more advanced pavilion of the topology optimization method. So so this pavilion, so this is the main design domain of the pavilion. Then we divide it equally divided into 4 pieces because it's symmetrical. So it's quite similar with the X-Form 0.1. So the different thing is this pavilion has a different height and more piece of the top. So we optimized the quarter of the pavilion again. Then we fixed the lower point of the column and added the normal pressure loads on the curved roof surface. So after run the algorithm, you can see the simulation in the mid of the video, and it's a biomimic structure simulated by computer with BSO, and it's quite looks like a nature growing branches. So on the right image is a quarter of the model, and it saved 52% of the material. So this image showing a quarter of the model is a 4.4 meter by 1.1 meter and 1.5. And so for the full model is 4 by 4 by 3. So after generating this model, we also tested in the Abacus to check the new structure of the pavilion meets the actual structure requirements. So it's quite successful. So what's the difference between the 2 pavilions? So X-Form 1.0 just have one flat top and just have also less branches. But the 2.0 has 3 different heights of the top and creating more branches. You can see the difference is more innovative and more complex. So this is different looking at the body of column. So we also print a small scale model. Then we divide it, and it's quite successful. So we divide it into the 20 pieces, and using the robotic to print the different pieces, and we deliver it from Melbourne to Barcelona to attend the ISS conference, because we just bring it by ourselves, so we only bring a quarter of model and assemble them in the conference site. So it's just 2 people with one 3D printer. Then we assemble it on site. It's just using the some screws. So this project is a large project in tectonic formation lab. It's called Cloud Effects. So the design of this project, the method is not using the topology optimization, but my contribution in this carbon fiber infused 3D printed tectonic project is the real-time structure feedback. So we published a paper in the conference of the digital future last year. So I used the grasshopper to creating the real-time structure feedback loop to analysis the real-time structure analysis at the same time, so we can fix and improve the design to match the best performance. So this is the video to showing the projects, and this cloud effect projects have been exhibited in Shenzhen Biennalia in 2019. It's also used the same machine to print the formwork of the plastic formwork, then cast the carbon fiber in the middle. So you can see the black thing is the carbon fiber structures. So this is the exhibition in Shenzhen, and it's a large team led by Roland Snooks, and the main research on this project is Hassan Mohammed, and we are all the team member on the project. It's a quite large project installation. And this project is called Cast Bodies. So Cast Body is also my own research project. It's using the aging bodies to create and interact together and to create a structure. And then we use the same method to print the plastic foam, but now the different times we use this plastic foam work as the sacrificial foam work. Then we cast the concrete, the high performance concrete into the foam work. So this is the final result. And later we can remove the foam work and keep the concrete structures as the complex form. Then we move on the robotic wire metal print to realize the same geometries. So because of the lockdown last year, we just collaborate with the Wollongong University to do this, to test this one cast body project, which is quite successful, and currently MIT Architecture already developed the one printing systems for the future projects. Also, when talking about the topology optimization methods using on my teaching results. So teaching, and I run the different workshop and the studios to test the same methods of the for the design. So this is the student work from MIT Architecture Design Studio. So students are using the Amoeba to do structure optimization, then run the swarm-based agent on the overall structure, then creating a PVDM within the landscape, and testing the structures. And then we use the plastic foam work and concrete to do the fabrication. And this is also another group of students to design an intricate wall system using the topology optimization method. And now I'm going to show you our digital future workshop in 2019, and the Amoeba video. You can take a look how the workflow of the BSO algorithm and the Amoeba.
Actually, Nick, can you possibly shut the music off so we can get? Yeah, thanks.
Yeah, so the girl designed the high heel shoes and do the optimization for the high heel of her shoes, and creating the tray branches structures under the shoe, and this is the cat tray, which students using the Amoeba to creating structure systems of a cat tray. And this student, the group of students designed the structure systems components. And this group of students optimized a chunk of Shanghai Tower. And this is the bicycle frame optimization. And currently we have several bicycle design using the amoeba, and that's more innovative. So this is end of the video. So last year, this is the Chinese heritage building design by a student in 2019. And this one is last year in Digital Future 2020, and a group of students designed Eiffel Tower 4.0. And this is last year's workshop in casual conference, and Xinyan and I lead the workshop and asked all the students to design, redesign the facade of the Sagrada Familia. And this is the successful staircase optimization design in the same casual workshop. So what is the new? So my research in the past few years, I'm also working on integrate topology optimization method with the swarm intelligence. So you can see the video here. So the left side is the BSO method on our building, and the right side is the swarm intelligence designed by Roland Snooks. So I'm developing with my team member to develop a swarm BSO. We call it swarm BSO based on the basic logic of BSO and integrate FEA model and the multi-agent behaviors. So we called it swarm BSO, and currently we changed the name to the motto, which is multi-agent based topology optimization. So this is basic rules, evolutionary optimization from the FEA and the strain energy density to the modify element property. So so we give a multi-agent a new structure behavior, a new behavior with the structure-based rules. So this is a basic agents movement, and we're working on the Python platform. So this is the very early results we test. So you can see the different performance using different parameters. So it's it's an agent-based topology optimization. So this research is to export a real-time structure behavior feedback loop in the process of designing intricate functional form through encoding BSO logic structure rules into a multi-agent algorithm. So you can see that each different steps of the iteration. And this is we test on the Bing system. So we published our paper is have been accepted and gonna be presented at casual conference next week. So our future work will apply the new algorithm on the lattice one staircase. So we just do some little tests, and this is future work this year. So I would like to thank Professor Maxi Roland Snooks and all the other colleagues give me the supporting in the past years. And if you have more questions, you can email me by the email address.
Thanks, Nick. That was terrific. It was great to see some of your new work. Really, really good. So we now have a chance to have questions. I'm delighted that Patrick Schumacher is here, and of course, Patrick's been very instrumental in pushing the notion of tectonism. It seems like it's a really hot debate everywhere. I mean, just one kind of comment I'd like to make before we start the questions. That is it's one of the most gratifying things to experience when you're an educator is seeing people emerging, individuals, some of your former students emerging so well. I actually remember when Akim was a student at the AA, he was a student just when I started teaching, everyone could see his potential there. He was called the Wunderkind by the other students. And it's incredible to see also the work coming through from Nick, Yassi and Dylan to see that the future's in good hands. So let's open up to questions. Welcome, Patrick. Just also the final thing to say that next Saturday we have Zaha Code and presenting some material on digital futures, which is going to be another astonishing session, especially looking at the relationship between Zaha Code and the AADRL. So let's have some questions. I think my first question would be for Dylan. I mean, I'm glad that you're monitoring the building and the Urbach Tower and its performance. What are you anticipating in terms of the behavior of the timber over time?
Neil?
Dylan, we can't hear.
Can you hear now?
Yes, yeah.
Okay. I mean, what we hope for in that case, unfortunately, in terms of investigating it, is that it doesn't move, because of course we have to have a building permit, and let's say we have a delicate relationship with the community to begin with, as let's say contemporary architects. So we don't want it to move. But why we're also really interested in this is that this hygroscopic movement is somehow theorized to be what twists a lot of these church steeples in southern Germany and Switzerland. So, and that's something that was sort of hotly debated, I think, in the 1920s and maybe earlier. There's like really detailed research in the archives of ETH as to why these, let's say, structural engineers trying to figure out why this happens. And usually they conclude that they think it's something to do with the underlying structure twisting because it dries out and goes through these cycles seasonally. And so we designed the tower actually to sort of counter rotate almost accidentally, so that if it does have this sort of seasonal shrinking, it will actually sort of hopefully, let's say, pre-stress or like actively stress back. So we're pretty interested to see how that works. With the furniture scale stuff, it's really a different story because there we don't necessarily lock it. We wanted to kind of perform a big movement and then really be something that is almost like a continued performance, which of course, again, if you think about furniture manufacturing, it's the opposite of what any furniture manufacturer, any producer wants to do. They want it to look right exactly like the picture, right? And where we're going is somehow something a little bit between these things that are growing themselves, I guess, over time. But even then, as soon as you cut off a growing system, right, you don't want to keep it living all the time. That requires a lot of energy and a lot of care. It sort of stops, right? And it's frozen, and then it goes into this sort of degradation. And I think with the chair, which we can't really show so much more now, but in 2 weeks maybe, the idea is really that it's something that over time shifts back and forth at different rates. And while it's not necessarily completely controlled or predicted, I think it kind of changes what we think of when we think of these designs. I mean, it will just keep living in a sense, right? Although it does not have any metabolic energy.
I mean, just picking up on that. I mean, so I assume as the moisture content in the atmosphere changes, so your chair will be become more or less a sofa chair. The shape will change a little bit, I guess. And I guess the other question would be so in terms of when you were to, if you were to kind of manufacture these chairs, in terms of kind of safety protocols and things, how would you guarantee? How can you guarantee its safety?
Well, I think we can, of course, like limit the range that it moves within, of course, right? But I think that it's also somehow alludes to some of the other work that we're doing, which is maybe not, of course, we're looking at responsive buildings. This is a really big thing, how the facades can move over time. And I think a lot of what Yazi is working on now is really moving now towards the sort of really testing in a building, right? That it's always moving, or in some cases that maybe there is a sort of interplay between a small, low energy control system that can kind of override or can tune the passive movement. So I think we're really moving towards something that's, I mean, we wouldn't be able to describe it completely as passive. I think that was maybe 5 or 10 years ago, and in some cases is super, super interesting. But looking at systems that really work together, right? So there is a sort of digital intelligence to it. There is a material intelligence to it. I think that's really where we're starting to go as we understand more and more about materials that we work with. But safety, I don't know. I mean, a heatherwick chair is also pretty dangerous, right? I mean, I've fallen off 1 or 2 of these, but.
I mean, I think it's fantastic research. Congratulations, guys. I mean, and I loved it when Achim first came up with this opening and closing of the timber apertures. I mean, remember this is, yeah, it's a pine cone, but it's also traditional barns and timber tiles. So there's a kind of vernacular lineage there, which is of course fascinating. And I do like now moving from natural material into 3D printing the mesostructure and developing these. And it was convincing when you said that, you know, we've done some, you know, curve folding, robotic folding, but when you have more intricate forms, it's actually, it's getting, you know, you can outcompete that clearly with your active self shaping. So that's very smart. We need to find the applications where we are requiring why these kind of pleating structures would be useful, and the intricacy is performing. It's an ongoing research, but congratulations, I really like it. I mean, I hope it's not only for space filling sandwich panels, because we're interested as an architects in also expressing this intricacy. And it leads me over to Nick. I mean, so, but you're prepared to do that because you have a very pragmatic in industry application set of mind. And if you invest in something this, it might also have these kind of, let's say, hidden uses, but it would be nice that this becomes visible in the phenomenology of the built environment. So I really am a great fan of that work, and I've seen it, you know, before, going from a natural material and then engineering the material more and more to and having a more let's say amplified also movement potential, etc. So both in terms of responsive environments, it's really strong, as well as in terms of you know, static element formation. So I really like that. I mean, I think, and I want to say to Nick, I mean, of course, there's a lot of going on in topology optimization, and I've just finished a whole studio on using this for tower design and tower clusters and so on. And we went through the different systems and compared the ways they work, and then translating that also in different materialities, which is the next step. In building scale, it's not about 3D printing, but you take these as guiding lines, and also analyze and how to translate these patterns into proper engineered structures, and then you go back and retesting it. I mean, I find that when you talked about the aesthetic pursuit together with this, I think we need to have the aesthetic has to follow. We have to kind of learn to like and learn to get an intuitive sense for what the optimal structures would and could and should look like. And I think there's intuitive control is quite important also to guide your research. I mean, I think in terms of your current research, there is the performance isn't hard enough brought to the research, and some of the elements, I mean, they look overstructured. And it's unclear in terms of the requirements of the structure. So there's a danger there. And I think what I think we have to remember is very powerful is that with these topology optimization, although we have more traditional engineering techniques can get at solutions for, let's say, symmetrical setouts, but what this is possible, and we're seeing this if you had something, a bridge or a tower where the load points or support points are irregularly set out, and also the loads would come in irregularly, and that becomes very tough and difficult to find an elegant solution with the systems. And I think that's where what is so powerful of the topology optimization is similar, where you go from, let's say, traditional vaulting and compression only to Rhino vault. The power here is that you can unleash it from point symmetrical or very simple geometries, and can have a free plan, more complex setouts, and then optimize for that. But it takes a lot disciplining. I mean, we've been worked on that, and to understand these results and cross-check them, remodel them, and then rerun the FE analysis to make them proper high-performance structures. And that's the thing where I think what I find powerful in the Stuttgart setup is that collaboration with Knippers and the engineering department. And maybe that's also something, I don't know if you have that in your setup, but I think it's critical. At DRL, we are also working with AKT directly, but it also has to be absorbed within the architectural, let's say, teams, that sensibility and will to make it proper performing, and then the aesthetic sensibility has to follow that. You can't make that an independent variable. That's would be my challenge to you.
I know we have a couple of questions from the group here. So I'll Marina, do you want to ask a question?
Yes, hello, good morning, everyone. It's a pleasure to have the opportunity to talk with you. I've been following your work in Stuttgart, or also the work of Nick, and his PhD, part of his PhD presentation. I'm a big fan of your work, and I have a question. I'm always having. I mean, one thing I was wondering about your process when I've been following the different processes is like. I mean, and it's a question I make to myself as well during my work. It is like, when is the time to be smart? When is the time to be clever? Or when is the time to be intelligent, or maybe just naive and work with certain ingenuity during these processes? So my question is like, what is the role of the failure in your processes? How you deal with it? Do you take advantage of the failure, or and even in terms related with Nick, for example? It's a general question for the three of you, but even in the Nick presentation, I was wondering what could be like the beauty of the failure during the process. So that's my question for whatever who want to jump to that.
Well, I think for us, I mean, of course, there is always a sort of variation, right? I mean, I think we also have to, when we work with these types of materials, we have to really reset, like, maybe our filter or our objective as to what is what's considered successful and what's considered sort of like put it in the wood chipper, right? But I think once that adjustment happens, I mean, I think we try to basically just learn, I guess, from every type of failure. I mean, I think if you ask Yazi, for example, she would probably tell you that everything she showed in the presentation was a failure. And that, I don't know, I decided that it was good enough to show, but she would prefer to redo it and I don't know, keep testing, right? But I think maybe what does not come out, and maybe that we need to also show that slide in the future, is the kind of like, I don't know, 600 bilayers that we test in order to understand the relationship between curvature and moisture content, or I don't know, between 3 layers of mesostructure and I don't know, different spacing in the mesostructure in order to understand that, because in so many ways it still is a sort of let's say hard science and hard trial and error effort when it comes to these materials. But I think that's also changing as we sort of shift from really wanting to have these analytical equations to explain everything, and more towards, I guess, the easier and easier to produce numerical models, and towards, I guess, even the sort of machine learning to try to figure out these multi-parameter problems where we don't necessarily understand why it works, but we know that certain combinations do work, right? Or how we can make it work. But maybe Yazzie wants to say something else about that.
Yeah, maybe what I wanted to add was that especially when you work with this type of materials that we work with that are not fully controllable, not fully predictable, I don't think anything is actually a failure, but it is that everything is just new. Maybe you did not expect that, so you could not predict that, but now you get to really dig in to see why this happens. And this is actually the cool part of the process, because you get to discover new things and move on.
Yes, quite similar as always. Yes, and Dylan, so just creating something new. And I think in the early stage, the topology optimization is just using by the structural engineers, and they're gonna use this method to reduce the material and do the material efficiency. But by accident, maybe they find it can create interesting structures, and then more architects start to use the topology optimization method to apply on the architecture design to creating something different. And now we are improving the this method. So like the Swampy, so we're using the agent-based topology optimization to creating something innovative.
I mean, just a comment. I was teaching at the University of Bath when the World Trade Center disaster happened, and I know that the engineers were absolutely fascinated by why the World Trade Center had collapsed in that particular way, and there was a whole conference about it. And I think to engineers, I mean, failure's important because then you see the limits of the structure. Jinan, would you like to ask a question?
Yeah. Thank you for the great presentation and the works. I'm following you guys for years, like the great works. I was doing some research on the digital fabrication timber and also on the metal 3D printing, like WAN technologies. And for me, what's interesting is about the design methods. I saw like you guys just like in the initial time, like we were thinking about the 3D printing fabrication. What is matches these techniques is like the topology optimization design methods. But like as Dylan did, is I think it's kind of new design methods, like you to simulate the timber materials by coding it, and I think it's a very interesting and a genius point. Like for me, I want the shape change of the timber. I think it's mainly controlled by the moisture content, and I'm curious about if this shape, is this the transform or it can shape reversible, like if the moisture content of the environment rise or decrease. So how can you control the shape of the timber in the whole life? I mean, if we use this technique to design a architecture.
I mean, I think that's you touch upon a really good point. I think it really depends. I mean, this is something that, of course, we have to consider in any building, right, that's made of timber. So that's also why there is so much research, let's say, about these types of things, because it's something that in everyday situations, somehow we have to take into consideration. I think what is really nice about our work now is that we're getting to the point where we can actually sort of choose, right? At what, like, where in the process we want to prevent it from shaping more. So in the tower, for example, like the process is designed so that it only shapes in the factory, right? And then while it's still in the factory, we put it together and we lock it into a very specific shape, right? So this is almost like the timid method, I would say, architecturally, of how to use this. And of course, it enables that we can produce, let's say, more sustainably, more efficiently, more effectively, certain types of geometry. But you're right, it's basically just touching the surface of what that might mean in architecture. So I think what we're working on in a lot of our future work, like with the furniture and with these types of responsive facades, is much more about, like, not necessarily pressing pause on that behavior or that movement, but really trying to integrate it into larger structures or larger buildings or larger types of systems. So it really becomes a part of the architecture somehow over time. And I mean, for me personally, that in the end is sort of the ultimate goal, to be able to somehow choose in a way when we want to, if we want to stop it, or if we wanted to allow it to sort of really play this long-term game of performance, right? And I think, I mean, well, we investigate that always really, really on the physical level. I mean, hands-on material level. I think that also somehow relates back again. I think, sorry, to what I think I was first introduced to somehow with Neil about these sort of swarm systems, which, like, I mean, it's always the question that, like, digitally you have this, like, incredibly sophisticated swarm system. And then, I mean, the question always for Roland Snooks, I mean, it was always, when do you stop it, right? And I think now we're getting to the point where, like, it's not just about where we can, let's say, stop it or press pause digitally, but also physically, right? And I think that's what's actually somehow really, really exciting. I mean, what we show now is the tip of the iceberg, right? I mean, it goes all the way to the sort. I mean, I would not necessarily say robotic architecture, but I think what I find fascinating is a sort of material robotic architecture. That's what I somehow think the future is. I think it's some sort of hybrid, right? But really moving into the physical, despite the fact that, of course, now the last year we operate almost completely digitally, we still somehow are placed into these different physical environments.
Thank you. I have a question. Yeah, thank you, all three of you, for sharing such a great project and lectures. Thank you so much. I really enjoyed, and I also felt a little bit nostalgic because I have been following your work a lot, and been doing this and learning these types of work a lot along. I think since I was student, and then recently, like, we have been just seeing a lot of, like, AI-driven projects, and that was a little bit like quite different from this type of kind of things. And I really feel like I also really kind of support the really material-driven kind of projects are really being developed and constantly, and I really, really appreciate that kind of sophistication and rigor. So thank you very much for sharing that kind of project. And I'm sure you were talking about a lot of failures and errors, and I'm sure what you present is just tip of the iceberg, yeah, of what you have done and achieved and figured. So thank you very much. And I want to just maybe, I'm sure this is kind of quite common, but I really appreciated what Dylan, you were saying when you were showing this image with a worker in the material lab, and talking about he has been gaining his also expertise and deciding things with his experience, and yeah, and that is something probably what robots or any machines cannot really still do, and during this kind of entire workflow. And I'm really, really curious, what are these kind of like crafts expertise, like maybe less about maybe like technical people, very technical people, like posing and making decisions in front of computer screen. But I'm really curious whether you have been encountered any like factory or kind of environment, and having people being engaged and the craftsmanship in being engaged, and their decisions have been very, very important. And I'm just really curious how that kind of roles are playing within this. And I often think it's that kind of things were not really explained and discussed within this a lot of like ICD papers, or like they always look very clean and neat. They look like they are like with really less human interference and produced directly out of clean processes out of robots. But I'm sure that's not the case, and I think you guys have gave us a little bit of tip of that today. And I'm just curious if you have any occasions you encountered, then we can what kind of things we can kind of really have that on the table and discuss in the future, to interfere and discuss that in our academic realm, so that kind of things are kind of more freely discussed and more openly discussed.
Yeah, I mean, I think that we are, I think we're pretty open in terms of science. I mean, almost everything that, at least that our group does is also published open source, and of a certain, let's say, scientific rigor that you should basically be able to reproduce it. I mean, I think that's something, at least in my team at ICD, has really been a sort of mantra in the last 2 or 3 years. And I think Yazi could probably also relate to the fact that this is incredibly time consuming. So, and also really takes a lot of patience in terms of, I mean, as architects, of course, we want to put the image, we want to put the video, but there's also somehow a lot of science that goes behind this, which I think if you want to know more, I mean, you probably know the publications, but these would be the things to look at, because I think what we usually show is a kind of quick, let's say, architectural and let's say almost concept theory description of what we do. But at least in our team, this is almost entirely backed up somehow through these publications. Of course, there's always a bit of delay with these, so so it might not be the things that are out now might not be, let's say, completely resolved or completely explained. In terms of like the kind of, I guess, robots and how these processes work, I mean, of course, our goal in general is also not necessarily to go towards 100% automation. I mean, I think if we want automation alone, then we would go to an automation engineer, and they could probably do it. I don't know, probably pretty expensive, but like you could get it done. I think what the point of a lot of our papers are to show the automation engineer actually that maybe their way of going about this, or the idea of just automating an existing process, is really not necessarily the most fruitful. So what we're trying to really show or to demonstrate is what happens when we, let's say, push these processes towards something completely different, or we rethink, let's say, the role of the robot in that process. I think we also have some of our research has also really shifted to be more collaboration in terms of humans and robots, but not just the sort of stereotypical human-robot collaboration, but also how these types of robotic systems or material systems integrate with existing methods of manufacturing for buildings, right? So, I mean, our robot in our lab is one thing, but as soon as we can put the robot in a sort of platform that can go into these different timber manufacturers that have their own existing, like, relatively deep body of knowledge and also body of digitization. So it's not that we're going back to the sort of like hand carving of wood, but we're sort of stepping in or trying to integrate or adapt into existing building construction industry to enable them to go, again, the sort of like big step further. So in our case, for what we showed today, this is mostly material oriented, right? It's like we're going in with a new approach to how to use the material. And in that case, with Bloomer Lehman, they're really amazing partner that really values the sort of work and the skills that they have. But even for them, it's a completely rethinking, right? Because every carpenter in Switzerland is trained to basically not work with the wood when it's wet. And what we're asking them to do is to actually do sort of half the process when it's relatively wet or moist, and then do the rest of their processing afterwards. So, I mean, the hardest thing in that type of process is really trying to convince these teams that are incredibly knowledgeable and incredibly skilled that they should rethink how to do it. But if you can convince them of that, and they see the results. So these types of teams, they only see things physically. So when they see the first pieces shaping, when they come out of the drying process, then I will tell you that they are 100% on board. But it's really the sort of like overcoming, I guess, these stereotypical types of processes. Maybe Yazi wants to also add something about that in terms of the 3D printing materials, because this, I think, is the same sort of thing. It's not necessarily that the architect is really going to the, let's say, filament production center and telling them to put something different in their filament. So maybe you want to talk about that, Yazi?
Yeah, so I actually I wanted to add something, and this was in my head, so maybe I didn't entirely follow your point, Dylan, but because I was trying to clarify this point in my own head, that I think this thing that you were talking about, that there is this sort of knowledge that a human would have when he is dealing with a piece of wood and something, and this is not necessarily a knowledge that a robot can gain or a robot can have. I think this is especially important in more of the initial parts of a research. So probably when you get to the production of one of the ICD pavilions, it actually is pretty much as clean as you see in the photos, because you can't really make like a nice and stable and precise Buga pavilion, for example, that the projects that were built 2 years ago, if you can't rely on the automated robotic fabrication process. But until you get to that point, there is a lot of tweaking. There's a lot of hands-on work that you as a designer and as a maker need to engage with it. So the way I see the process that I myself follow is that I need to be able to do digital things. I need to be able to do code, to program, to read the G code. I need to be a little bit able to deal with hardware, to like tweak the 3D printer to some point. But most importantly, I really need to be able to get hands-on with the material, with the things, and build many iterations and really see how they behave, touch them with my hands. So I think it's really a cool combination of everything digital and everything manual, especially when you're in the research stage. That's really necessary. None of them can do it on their own.
I've got a question. If no one else has one, Dylan, you mentioned in the Urbach Tower how you'd want to maybe use a transparent timber for the roof light, as it were. What struck me is slightly, I wouldn't say jarring, but the fact you had a steel plate at the top. I mean, could you get rid of the steel at all? Is that part of your agenda?
I think we probably could get rid of the steel structurally, but I mean, we still need something to basically interface between the wood and the polycarbonate in that case. So I think this also has a bit to do with, I guess, negotiating the boundaries between something that is really a building demonstrator of relatively unproven manufacturing technology, and of course, wanting it to also be a sort of building that the public can really take advantage of, right? Because if the thing is gone in 1 or 2 years, then it also doesn't necessarily serve its purpose, right? It might, in some ways, actually sort of put the technology in a tricky spot, right? So I think the steel is not part of our agenda, but in that case, we needed it. But this helps, I mean, just very marginally structurally to align the structure, but it basically is like a sort of wire that brings the lightning protection system like basically through the roof and into a cable that's embedded in the timber and down to the ground, which for something that is in a field like this and very exposed is some sort of major design consideration that we is something I had never somehow dealt with yet. But what we do manage to avoid is that, okay, of course we have steel screws, right? But these can be taken out, but we don't have any, we're able to basically tweak the detailing in a way parametrically that we can avoid needing a steel plate, for example, over the openings, which would be the sort of classic classic structural problem, right? So we want to use less and less steel. I think we could have made the top probably out of hardwood if we really wanted to, but for now we use this sort of very thin steel part. It also protects the top, which has the sort of end grain from the water, which is quite nice. And the whole structure is also built to basically be taken apart. So it has sort of connections that are made specifically so that it can be taken down and at the end of the 10 to 15 year building permit, and then either put up somewhere else, or I don't know, we're open to ideas what to do with it. We thought maybe we could also sort of then re-CNC this into high-end furniture or something like this.
Maybe a quick question for Yassi. I mean, some of those cute little elephants you were showing. I guess I'm wondering whether the intention eventually is to actually manufacture objects. I'm thinking here both of the aspirations behind the Bauhaus. Maybe they didn't produce as much as they would have liked, but also the Perry Hoberman. So the Hoberman ball, which became a toy. Is there an aspiration to kind of produce these elephants or toys out of this eventually?
You should show the Christmas tree, Ezzy.
I should show what?
The Christmas tree.
Yeah. Yeah, we also have a Christmas tree that self-shapes. So I don't think specifically the elephant. I mean, maybe Dylan would also want to talk about this. Not necessarily as a product, but elephant for us is a really good way to first like explore some different ways that we come up with from time to time to see now how this method would look to like make some sharper folds on the elephant. And yeah, it's a fun prototype to work with, but I don't think that, I mean, maybe maybe Dylan has some plans for the elephant.
I don't know. I think the elephant is, of course, it's in many ways is a sort of Stanford bunny of self-shaping. I think we can discuss this also with Skylar Tibbetts probably for many minutes. But I mean, we've taken this always almost accidentally as kind of the object in which we test our different material systems. So we have, of course, these apertures, which are a part of a lot of exhibitions where we use this to test the motion, but this kind of like self-shaping from flat, we really use the elephant. But of course, we would really like to build one out of wood as well. This is definitely possible. So I don't know, maybe now that I have a bit of free time, this is what we do. But I think also it's maybe important to mention that we really, I mean, we gear towards building systems. So I mean, I think this is a testament to Achim's kind of dedication and let's say focus that the sort of like almost toy systems are what we do in our spare time after we build the towers and after we build the shells. And I don't know, even furniture is somehow really on the boundary of what we do, right? I mean, we're not, in the end, we are architects. And I think the challenge for architects is also somehow very great. And I think that's also where we have the potential to have a really large impact in the future. But of course, we would love to sell some of our products or send them out in the mail. I think the kind of like Heatherwick Christmas card is kind of something we would really maybe need to regenerate or reinvigorate in ICD.
I've got a question actually that came, well, it was in the chat from Matthias, who unfortunately, Matthias Del Campo, that is, unfortunately his Wi-Fi broke down, so he wasn't able to carry on. But it's a question about scale, something that I've been looking at myself, and in a sense, I mean, the question maybe I could direct it towards Nick, especially the context of the structure, and that I know it wasn't done by Mike Shi, but that big structure in Japan, I think it was for Toyota, maybe, I don't know, or Arata Isozaki, I forget. To what extent, I mean, I always have problems. I think scalability is a very dangerous word because things don't scale. You know, there are logic behind this, and Philippe Bloch also talks about this. But how does scalability fit in, especially with in the context of what you're doing, Nick, in terms of amoeba and so
on? I think the Japanese architecture, the one I show as Qatar Convention Center, I think this is a large scale for the topology optimization project right now. But what I'm doing is just creating the architecture components, because you can't create the full building using the topology optimization methods. So we can just creating different components using this method to assemble them, and maybe like part of the facade design, the staircase design, and column design.
Yeah, hi Nick. I got a specific question for you, like for the WAM techniques. I do some research on it, like WAM technique compared with other 3D printing metal 3D printing techniques is high efficient and low cost, and it has no geometry limitation. But it seems like this technique is still not very suitable for architecture, because like in our industry, the cost requirement is very sensitive. We need very low cost. So I think maybe we can put a discussion here, like how where can we apply the WAM techniques, like in which formation, like in nodes or some connections or other types of elements, I'm not sure because I'm still searching on it. How these techniques will develop in architecture field. Yeah.
So yeah, we also just start the one metal printing, and currently the benefit for the one metal printing is it's not too obvious because it's the printing speed is quite slow and also creating a lot of problems. And sometimes the 3D printing structure or the object cannot be certified by structural engineers. But we're trying to use it to creating printing some intricate forms. So it's instead of making the molds making the molds or the traditional way to make metal objects, metal components, we're using the additive manufacturing method to creating some intricate forms using one metal printing. This is only the test and the very new method. Yeah, we're still working on this research.
Do we have any further questions? I mean, this has been a terrific session. I've got to say thank you so much. It's been really mind-blowing to see all this work. Any final questions? I mean, in some ways, this is a debate that's going to continue, and it's really amazing to see the kind of genealogy in all these things. I mean, just to go back to my comment before, I remember when Akim came to USC. I don't know if Dylan was in the workshop at the time, but we had Manuel de Landa there, and Manuel hadn't met Akim before, and he kind of looks at him and said, "That's Fry Otto 2.0." So, but it's great to see that what's going on now in Stuttgart in terms of that tradition kind of taken further in some ways. I always see Akim somehow as a kind of a version of what is that? Oh, Fry Otto. Okay, I think that we should wrap up now. It's I just want to say that I've really been blown away by some of these presentations. It never ceases to amaze me the kind of the rigor of the works coming out of ICD, and somehow Akim's attracted so much talent there. I used to teach with Tobias Schwinn when I was at Dessau, and he's also part of the team, and Tiffany's there as well. So it's really great to see that work. It's also great to see the work that Nick has been producing, the next generation of that work, and fabulous to see that he's now a colleague of Roland Snook and Mike Shee, and we look forward to seeing some more. Let me just finish up by saying that the material intelligence is, of course, the is the theme of the Digital Futures Conference. The closing date for submission is April the 15th, and anyone out there would like to submit something, please do. There will be a series of workshops this summer. We are just planning them at the moment. Just to repeat, there are going to be some hybrid workshops where fabrication will take place in Tongji, and collaborations will happen between a number of institutes in around the world, including RMIT, including ICD Stuttgart, and there'll be some online workshops as well. So this is all very exciting, and Philip and I are also trying to plan something in terms of a doctoral platform that might take some form over the summer as well, as a place where we can further exchange doctoral ideas. But I think today was real evidence to my mind of how significant we can use this platform can be. We can use it to exchange ideas across the planet. And really interesting ideas. The only challenge, of course, is for Nick. I just want to point out for him, it's, I don't know what, 3:30 in the morning or something in Melbourne. So I just want to really especially thank Nick for staying up so late. And let's look forward to some more collaborations over the summer. And thank you also to Patrick and Samin and Janan and Marina and others for their questions. This will be uploaded both on Bilibili and on YouTube as a permanent resource, as are all the other sessions. And hopefully this will, we're leaving a legacy out there. And I also want to say that this has been a live stream, so there are students all over the world who have been following this. I know that there's some in Egypt, so it's great to be able to share these ideas in this way. So thank you, Sheshe, merci, and hope to see you all again soon. Thank you, everyone. Thank you.
Thank you.
Thank you very much.